Okay, hey, welcome back. We're now into alternating sequences. So what's special about this is we'll be able to, whoops, this is 9.5. So what, I can't edit this. What's going on here? 9.5. Oh, come on. 9.5 alternating. Did I spell that right? Sequences. Okay, so the deal with these is before this point, all the sequences we were dealing with were positive term sequences. So for the integral test, you needed all positive terms. For the limit comparison test and the direct comparison test, you needed all positive terms. Now we're going to start generalizing, and the first generalization is introducing the alternating sequences. So the two forms we're kind of looking at. And we always assume that this a sub n portion is positive, but the two forms, you'll see this -1 thing kind of in there, times then the a sub n portion. And we're going from n equals 1 to infinity. In this case, you'll have negative odd terms, so negative a1 plus a2 minus a3 plus a4, etc. And then the other version, obviously, not much of a shock. This is the version when we have the even terms are negative. Okay. Okay. We'll have the alternating series have their own test for determining the convergence or divergence. It's called the alternating series test. It's pretty simple to do. It's basically, if you we'll assume again that the a sub n portion of the series is greater than 0. If that's true, then the alternating series will converge if the following two criteria are both fulfilled. So first off, the limit of that a sub n portion has to equal 0, again, as n goes to infinity. And then secondly, you have to show the a sub n terms are monotonic. In particular, they have to be non-increasing, okay? In other words, decreasing. So you have to show that a sub n plus 1 is less than or equal to a sub n. It's better if you could show it's less than, but less than or equal to will do the job. In 9.1, I gave you 3 sort of ways to do this. So the first way, do a ratio of a sub n plus 1 over a sub n and show that's less than or equal to 1. The second way was to subtract. So a sub n plus 1 minus a sub n, you need to show that that's less than or equal to 0. And then the third way was kind of the calculus way. Just replace f of n, a sub n with f of x and take its derivative and show that was less than or equal to 0. Okay. I covered those tests for monotonicity in section 9.1. So you may need to go back and review those. Okay. Let's go ahead and apply it, and then we'll talk about the proof. The proof is a bit long-winded, so let's go ahead and dive into maybe just working with some examples first. Okay. Okay. So I'm going to go to my book. I haven't done these beforehand, so hopefully I won't get myself into trouble. Let's look at number 11. So we have the sum of -1 to the n all over 3 to the n. From n equals 1 to infinity. And so, first off, we want to show the limit of the terms of this a sub n portion. So first off, the a sub n portion does not include that -1 to the n thing there. That's not included. You're just looking at 1 all over this part, the 1 over 3 to the n, as n goes to infinity. And this will go to 0. If you think of it in terms of sequences, 1 over 3, 1 over 9, 1 over 27, 1 over 81. It's an L over infinity form, so that will go to 0. Secondly, then, you need to show that a sub n plus 1 over a sub n. The way I like to do it is usually using that first method. Okay, you'll see different methods, of course, in the book, but this is kind of my go-to method. So anyways, a sub n plus 1 over a sub n. Come on, just give me a sub n equals, and again, the a sub n portion, when you take this sum, and you can rewrite it if you don't see it at first, the a sub n portion of this is 1 over 3 to the n. That is your a sub n. Okay, cannot reiterate that enough. So anyways, a sub n plus 1 is 1 all over 3 to the n plus 1. And then a sub n is 1 all over 3 to the n. So to divide by a fraction, you're really multiplying by reciprocals. So times 3 to the n all over 1. 3 to the n over 3 to the n plus 1 is the same as 1 all over 3. And then you compare that to 1, and clearly that's less than 1, so that's good. We've shown the limit is 0. The sequence the sequence of the a sub n portion of the series is decreasing, and that implies it's convergent. Okay, so hence it's convergent. Okay, let's look at a couple more of these. I got to sneeze here. Oh, great. Hold on. Continue. Okay. Hopefully that's not the beginning of COVID, but here we are. Let's look at number, I guess, 15. And we have the sum from n equals 1 to infinity of negative 1 to the n times n all over the ln of n plus 1. Okay, great. So first off, I'm going to take the limit of the a sub n portion. So it's n all over ln of n plus 1. As n goes to infinity. So this thing is it's infinity over infinity. Okay, so we do L'Hopital's. You'll have 1 all over n plus 1, which is the limit as n goes to infinity of just plain old n plus 1, which is infinity. It's not equal to 0. Technically, you can't say it's divergent because you're not really done the nth term test. The nth term test would verify that it was divergent, though. So note the nth term test. You would have the limit as n goes to infinity of the whole thing, the n negative 1 to the n as well. Basically, you could show that the even terms go to infinity, the odd terms go to negative infinity. In other words, the limit of this thing does not exist. In other words, the thing does not equal 0. In other words, it's divergent. So in general, you can kind of skip this part, showing that by the nth term test. I believe that if you get an infinity in the first step, it's going to automatically imply that it's via the nth term test. It will imply that the series diverges. Okay. Okay. Let's look at another one. So this is number number 23. We have the series n equals 0 to infinity of negative 1 to the n all over n factorial. So first off, the limit of 1 all over n factorial. Again, we're not looking at the negative 1 to the n portion. Okay, so the limit of this thing, clearly it's L over infinity, so that will go to 0. And then secondly, again, I'm going to do this kind of ratio of a sub n plus 1 over a sub n. These factorial terms kind of have recursive definitions. So what is a factorial? So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. In other words, 7 factorial is actually equal to 7 times 6 factorial. And in general, then, if you have n factorial, you could say that's equal to n times n minus 1 factorial. So if you have n plus 1 factorial, that's equal to just substituting n plus 1 everywhere into this expression. You get n plus 1 times n plus 1 minus 1, which is n factorial. And so I can use that idea to simplify my factorial expression here in step 2. So I'll have the complex fraction turns into multiplication by reciprocals. And then I have n factorial all over n plus 1 factorial. And then you could use this definition here to rewrite the denominator. Okay, and then you could remove the n factorial portion. And you just get 1 all over n plus 1. And then you're comparing that to 1. If it's less than 1, then it's decreasing. And certainly for n greater than 1, greater than or equal to 1, this will be less than 1 because you got something small over something bigger. Okay, so this one is convergent. Hence converges. Let's look at another one. Let's try number 25. You have the series of -1 to the n plus 1 times the square root of n all over n plus 2 from n equals 1 to infinity. Okay, so again, I'm taking a look at the limit of the square root of n over n plus 2. As n goes to infinity. This is an infinity over infinity, but it's kind of one of those polynomial types. So you could just look at the ratio of square root of n over n and figure out that limit, and they'll have the same limits. So square root of n over n is the same as 1 over square root n. And then as n goes to infinity, that will be L over infinity, so that will be 0. Secondly, then you want to show it's decreasing. So again, I'm going to make a ratio, n plus 1 all over n plus 2. So I replace n with n plus 1. So this will be n plus 1 plus, is it really 2? Yeah, okay, well, whatever. And then divided by a sub n, which is square root of n all over square root of n all over n plus 2. Okay, so we can rewrite this square root of n plus 1 all over n plus 3 times n plus 2 all over square root of n. Then we can, I guess, rearrange things a little bit. So we have n plus 2 all over n plus 3 times the square root of n plus 1 over the square root of n. And then we're trying to compare this to 1, right? The problem is we have this thing, which is less than 1, and then this thing, which is greater than 1. Okay. Yeah, and right here, this is probably going to be a pretty big leap of faith, but I wouldn't expect you to do something like the following on the test or something like that, but it might have been easier to go with a calculus test here, like get the derivative and show that was less than 0. But if you want to see how to do it this way, I guess you could say, all right, n plus 2 is the same as n plus 2 squared square root of, then times the square root of n plus 1, and then you have all over n plus 3 squared square root of times the square root of n. So it kind of gets rid of the square roots, and all you're doing is comparing polynomials to see if the top is less than the bottom. So we have n plus 2, this part squared, is going to be n squared plus 4n plus 4. And then the product rule for radicals, the product of radicals is equal to the radical of the product. So then times n plus 1 all over the bottom, which is going to be n squared plus 6n plus 9 times n. And I had to pause the video even to think this through. I'm not thinking this off the top of my head. But anyways, the numerator at that point, if you were to factor that out, would be n cubed plus 5n squared plus 8n plus 4. And then down below, you'd have the square root of n cubed plus 6n squared plus 9n. And then to show it's less than 1, you just need to show that the polynomial in the numerator is less than the polynomial in the denominator for n values greater than or equal to some n value like 1. So note over here to the side, I'll just kind of show why that's true over here to the side, and it will be less than. n cubed plus 5n squared plus 8n plus 4 is definitely less than n cubed plus 6n squared plus 8n plus 4, which is definitely less than n cubed plus 6n squared plus 8n plus n, when n is greater than 4. And then you got it, right? Because that's equal to n cubed plus 6n squared plus 9n, which is the denominator. So the numerator is less than the denominator, therefore that expression is less than 1. If you take the square root of it, it'll still be less than 1. Okay. So that proves it's the limit goes to 0, and it's decreasing, hence it's convergent. Okay. So you're probably not used to thinking in this kind of algebraic way. If you take like computer science, they tend to actually teach that sort of thing when they're teaching order of algorithms. Okay, so they have to kind of teach you how to do that stuff. But you've probably not seen it before unless you're big into algebra and maybe you were in a mathlete in high school or whatever. Anyways, I want to look at one more nasty one. I'm sorry to show all the hard ones here, but sometimes I do just easy ones in my lectures. I want to do some hard ones, right? So n equals 1 to infinity of negative 1 to the n plus 1 times n factorial all over 1 times 3 times 5 times dot, 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 all the way up to 2n minus 1. Okay. So the hard part for this one seems to be showing that the limit is going to 0. So that's kind of the first thing to tackle. The n factorial all over 1 times 3 times 5 dot, dot, dot to 2n minus 1. Okay. And I think the squeeze theorem is going to get it done. So first note that n factorial all over 1 times 3 times 5 dot, dot, dot to the 2n minus 1, that'll be greater than or equal to 0. Just put 0 over there. And then to make the boundary on the top, notice that this way you can pair these things, right? So how many things are in the numerator? How many things in the denominator? There are n things up here, and then there are n things down here. So you can do this kind of pairing with each term. You could say n goes with 2n minus 1, and then n minus 1 goes with 2n minus 3, and etc. Okay, so down all the way down to 3 goes with 5, 2 goes with 3, and then 1 goes with 1. Okay. The thing to notice about this sort of, if you think of it as kind of a sequence, a product of a sequence, the terms are decreasing, or rather, sorry, the terms are increasing, right? So if you look at n all over 2n minus 1 and compare that with n minus 1 all over 2n minus 3, you can cross multiply or just multiply both sides by the reciprocal of that thing, and you get n times n minus 1 all over 2n minus 1 times 2n minus 3, and then that thing will equal n squared minus n all over 4n squared minus, did I do that wrong? Yeah, I multiplied wrong. Oops, sorry, reciprocals. So in the numerator, it's n times 2n minus 3. So you get 2n squared minus 3n. In the denominator, then you got a FOIL, 2n minus 1 times n minus 1. So you're going to have with 2n squared minus 2n minus n, which is minus 3n, and then plus 1. So clearly that denominator is 1 bigger than the numerator, so it's less than 1. In other words, as you go from this first term to the second term, it's increasing. And so it increases, increases, increases all the way up to here, right? So we could say that this expression is definitely less than or equal to, well, every expression, every term here must be less than 2/3, right? So I could kind of replace the first term with 2/3, and then So this thing will be less than this thing. And then I can replace the second term with 2/3 because, again, this thing will be less than this thing, right? Okay, hold on. Okay, so you could see this thing is decreasing, and each one of these terms is less than 2/3. So you can multiply, keep multiplying by 2/3 times 2/3 times 2/3 dot 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 times 2/3. How many of these are there? Well, there's n minus 1 of them. Okay, so the last one, times 1 then. But if you simplify it, so let's box this material off, it'll equal 2/3 to the n minus 1. Okay. Okay, so then you can take the limit on both sides, right? You know the limit of 0 on the left as n goes to infinity is 0. That equals the limit as n goes to infinity of 2/3 to the n minus 1. So long as this ratio is less than 1, if you take that ratio to n or n minus 1 or n plus 1, you're going to end up going to 0. Okay, so you got the limit on the left and the right going to 0. That implies the limit on the middle goes to 0, and hence this limit here will equal 0 by the squeeze theorem. Okay. In other words, see below. And I would never ask you to do that on a test. It's just every once in a while it'll come up in homework problems, and you may be mystified as to how to do it. And hopefully that kind of argument helps you at least a little in your understanding of the subject. So, anyways, I think that's really as hard as I've seen them get. Let's talk about the proof of the alternating series test and why we need these two criteria. Okay, so a lot of times when we start getting more and more tests, you might make false kind of observations. Like you start saying, well, because the limit here goes to 0 in this test, and that was convergent, then I must be able to conclude over here in this test, if the limit goes to 0, it's convergent too. So it's like you can't think in that way. You can't think in surface terms. You always have to kind of go to the proof, and the proof is why the criteria hold. So let's look at the proof a little bit. The proof is not fun. And there's kind of some little helper facts that we need along the way. So I hope you could take these for granted, but sort of one helper fact, and sometimes they call these things lemmas, these helper facts. Lemmas is a little animal that jumps off of cliffs. So lemma, if the limit of a sub 2n as n goes to infinity equals 0, then the limit of a sub n as, did I get this backwards? No, it's backwards, sorry. If the limit of a sub n equals 0, then the limit of a sub 2n will equal 0. Okay. So if the limit of a sub n is going to 0, and the way you think geometrically usually, so a limit means that for any epsilon around some number you pick, as long as you go out far enough, all the terms of the sequence will be really, really close to that number L, right? So at first maybe they're jumping around here, but then once they get past this thing, they'll be within that epsilon region. Okay, so if that's true for all of the terms, it's definitely true for the even terms. Okay, so hopefully that kind of convinces you of that fact. Another fact is if the limit as n goes to infinity of a sub 2n equals the limit as n goes to infinity of a sub 2n minus 1, and that equals some number L, then the limit of a sub n as n goes to infinity will also equal L. So here the idea is that there'll exist some point like n. Once you go beyond that point, all of the even numbers will be within that epsilon distance. And then, so that's this part. And then this part says there exists some other n value, say n1. Once you get beyond that, all of the odd terms will be within that epsilon value. So therefore, if I get beyond whichever one of these n's and n minus n and n sub 1s are bigger, all of the terms will basically be within an epsilon, because all terms will either be even or odd terms. And hopefully then that kind of thinking is going to convince you that this statement is true. Okay, so we have this kind of truth, this truth. Another truth, again, is the old, if something is increasing and bounded above, it's convergent. And that was a 9.1 factoid, increasing and bounded above or decreasing and bounded below. We use that non-increasing, non-decreasing stuff, but it's so confusing that I'm just going to, if you allow me to, just say increasing and decreasing instead of the other one. Okay, so we need these kind of helper facts to prove our theorem. And again, the theorem has two criteria. So in our proof that, and what are we trying to show? We're trying to show that the sum, the series equals something. So it adds up to something. In other words, it's convergent. Okay, so there's two things we suppose that we need for this proof to work out. So we're going to suppose that the limit of a sub n as n goes to infinity will equal 0. And, well, actually, there's three things we need to suppose. The first things first, so these two facts. Limit is a sub n goes to 0, so n goes, yeah, okay. And then, what else? A sub n plus 1 all over a sub n crud, speed that up. The thing is decreasing, okay? And a sub n is decreasing. In other words, a sub n plus 1, the next one is line is less than or equal to a sub n. Oh, and we also need a sub n is positive. Okay, so I think all of that plus these three little helper theorems will kind of get the job done. Okay, so what, our goal, what we want to show is basically that the series is convergent. And a way to show that the series is convergent, so if we have the series -1 to the n, and we're going to work the n plus 1 version, so all of the even terms are, all the odd terms are positive from 1 to infinity of a sub n, which is equal to the limit as n goes to infinity of, or I guess we have to use some other letter I goes to infinity of the sum of -1 to the I plus 1 from I equals 1 to n. Sorry about the n's and the i's and junk. But basically what we have to show is that the limit as, whoops, this would be n then. The limit as, let's make this I right off the bat. I am so sorry. So this would be I, this would be I. And I lost my a sub I here. Okay, so this is a sub I, this would be I plus 1, this would be I. Okay, so the limit as n goes to infinity of that thing, we're trying to show that that's equal to some number, so it's convergent. What is this thing? This thing is a sequence of partial sums, right? It's that S sub n thing. We're trying to show that the sequence of partial sums, S sub n, as n goes to infinity, is equal to some number. We could call it S or whatever. Okay. In other words, it's convergent. So the goal is to show that this thing equals some number S, which will show that it's convergent. Okay, so what we're going to have to do then is play around with that S sub n thing. We need to play around with this and to show that thing is convergent. Okay, the sequence of partial sums. So first off, we're going to note S sub 2n, believe it or not. So note the sequence of partial sums S sub 2n. In particular, let's expand it. So S sub 2n would be a sub 1. The odd terms are positive, minus a sub 2 plus a sub 3 minus a sub 4 plus ... all the way up to a sub 2n minus 1 minus a sub 2n. Even terms are negative. Okay, we could take this thing and associate all of these terms together. Okay? And then we notice all of these terms, because the terms of the a sub n terms are decreasing, all of these terms will be positive. Okay, so positive, positive, positive. In other words, as we move from s sub 2n to the next term in line, which would be s sub 2 times n plus 1, which is, of course, just s sub 2n plus 2. That's the next term in the sequence of partial sums we're looking at. S sub 2n plus 2 is really just s sub 2n plus this additional positive thing. It'll be a sub 2n plus 1 minus a sub 2n plus 2. Okay, and this thing is positive. In other words, the sequence s sub 2n is increasing. Okay. Also, then we can kind of look at the s sub 2n in a different way. We could say s sub 2n is equal to a sub 1 minus, and then factor out the negative from the next two terms, a sub 2 minus a sub 3 minus a sub 4 minus a sub 5 minus dot 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 minus a sub 2n minus 2 minus a sub 2n minus 1, and then finally minus a sub 2n, right? So what? Well, because these things are decreasing, a sub 2n will be greater than a sub 3. A sub 2 will be greater than a sub 3. So this thing is positive, and basically what we're doing is taking a sub 1 and subtracting away a bunch of things. Okay, if a sub 2 minus a sub 3 is negative, we would be taking a sub 1 and adding in a bunch of stuff, but it's not. It's positive, so we're actually subtracting away everything. In other words, s sub 2n is bounded above. The sequence of partial sums s sub 2n is bounded above by, believe it or not, a sub 1. Okay. In other words, the sequence of partial sums here, this s sub 2n, is increasing and bounded above. In other words, s sub 2n is convergent by that theorem from 9.1. The monotonic bounded sequences are convergent. Okay, it's convergent because it is bounded above and increasing. Okay. Okay. So, anyways, we have that fact. So what? Well, now consider s sub 2n minus 1. Okay, the s sub 2n is like a sequence of even terms, and s sub 2n minus 1 is a sequence of odd terms. Okay, if we can show that s sub 2n and s sub 2n, the sequence s sub 2n minus 1, are both convergent to the same thing, we could say then that the sequence s sub n converges to that, whatever that thing is. Okay, so now consider then this new sequence is the terms of the sequence s sub 2n minus 1 terms are going to be equal to kind of s sub 2n, right? So it's just s sub 2n minus one of them, because if you look at the at s sub 2n, what is it? Well, it's just s sub 2n minus 1 right here, minus a sub 2n. So s sub 2n minus 1 should equal, if you just add a sub 2n to both sides of that statement, s sub 2n minus 1 will be s sub 2n plus a sub 2n. Okay, so s sub 2n minus 1 will be s sub 2n plus a sub 2n. And then we can take the limit on both sides. Taking limits, we then note the limit of s sub 2n minus 1 equals the limit of s sub 2n plus a sub 2n. Okay? And we know both of those limits converge. Basically, a sub 2n will converge because a sub n converges, and that was the second fact. If a sub 2n, oops, sorry, it's the first fact. If this first part is from the supposition, the limit of a sub n equals 0. That's like the first step in our criteria for showing something is convergent if it's alternating. So we already had that supposed, the limit of a sub n equals 0. So thus, from this little lemma fact, the limit of a sub 2n will also equal 0. Okay, so we had supposed this. So both of these limits exist. And we showed the limit of S sub 2n has to exist because S sub 2n, the sequence of partial sums, is convergent. Okay, so both of these parts exist, and in particular, we know a sub 2n is 0 from our assumption, so we just end up with the limit of S sub 2n, which we know converges to some number L. So the limit of S sub 2n and the limit of S sub 2n minus 1 equal the same thing, which is the second lemma. Right? So if the limit of S sub 2n equals the limit of S sub 2n minus 1 equals L, then the limit of S sub n will equal L, and that's kind of what we wanted to show. So hence, the limit of S sub n will equal some number L, and hence that shows us that, hence the sequence of partial sums is convergent, and so that means the series from I equals 1 to infinity of -1 to the I plus 1 times a sub I is convergent. Look, right? It's kind of a mouthful. Anyways, if nothing else, I hope you appreciate that proofs are kind of more difficult than just doing math. In my opinion, a lot of it just comes down to kind of saying the common sense part, kind of nailing down the mathematical common sense, and that's hard. You imagine trying to get a computer to do that. Okay, I think that's a lot harder than getting a computer to do integrals, right? So, anyways, that's that. The next part, then, if you know it's convergent, you can actually get approximations. So in the case of the telescoping series and the geometric series, we could actually figure out the sums. But for the integral test, we were only figuring out if it was convergent or divergent. For the limit test, limit comparison test, and the direct comparison test, we could only figure out if it was convergent or divergent. Okay. With alternating series, we can actually get approximations of the sums. Okay. So section 3, alternating series estimation theorem. We start out with this theorem that says that the difference between the actual sum and the nth partial sum is less than or equal to the next term in the a sub n sequence. Okay, I forget which theorem it is. Let me figure that out real quick. And there's still more to do after this. This is such a long section. It's theorem 9.15. Okay. So this would be basically if your alternating series is convergent, then the difference between the actual sum and the nth partial sum, which is kind of thought of as the remainder, will be less than or equal to the next term in line. Okay. Okay, so let's make this a little bit more clear. I have a sequence which I know is convergent, like -1 to the n over n factorial. That guy is definitely convergent. We proved it above. And you could start at 0 if you wanted to infinity. Okay, the difference between the actual sum and the nth partial sum. So we need to figure out what these things are. Is less than a sub n plus 1. Okay, so what is S sub n? So S sub n is just the first n terms of our series. So in this case, you plug in 0 first to get negative 1 to the 0, which is 1, over 0 factorial. 0 factorial is 1, so 1 over 1 is 1. And then plugging in 1, it'll be minus 1 over 1 again, and then it'll be plus 1 over 2 factorial, minus 1 over 3 factorial. Let's make this a little more concrete. Instead of going to n, let's just say 5, right? So 1, 0, 0, 1, 2, 3. So there's 5 terms. I'll presume that S sub 5 means that there's 5 terms. And of course, the book has strategically avoided that issue, leaving me to kind of guess. And I'm going to say S sub 5 equals the first 5 terms from 0 to 5. Okay, so and then this will be plus 1 all over 4 factorial, which is 4, minus 1 over 5 factorial. Okay, so the theorem is saying that basically S minus S sub 5 will be less than or equal to the next term in line, which would have been 1 over 6 factorial. Okay, and you don't include the negative because you're just talking about A sub n. So the difference between the actual sum and this fifth partial sum is going to be pretty small, right? 1 over 6 factorial, I don't know what that is, let me figure that out. 1 divided by 6 times 5 times 4 times 3 times, of course this is hard to plug in, 3, delete, 4 times 3 times 2, 2 is 0.0014-ish. Okay, that's pretty small, right? So it's saying that basically now you can kind of just use the first couple terms of your sequence to determine an approximation. Not only that, you can figure out how good the approximation is, okay, so long as this thing is convergent. Okay, so let's apply this. And there's basically 2 versions of this. One version, you're trying to see how good your approximation is given some value of n, like S sub 5 is within 0.0014 of the actual sum. The other question is, given an error, like instead of 0.0014, like 0.005, given that error, how many terms, how long does your partial sum need to be in order to be within that error? Okay, so those are your 2 types of problems. Let's look at one of each, and then there's still another kind of issue with regards to absolute and conditional convergence. Okay, so anyways, approximate the sum using the first 6 terms. So how good is this approximation, basically? So here's an example. We have the sum of n equals 1 to infinity of negative 1 to the n plus 1 times n all over 3 to the n. Okay. Let's presume it's convergent. I believe I've showed above that it was convergent. Well, let's go through it anyway. So first off, the limit of a sub n, which is n over 3 to the n, that's L'Hopital's, right? So infinity over infinity, I can go limit of 1 all over 3 to the n ln3, which is 0. So good. Secondly, then, I like to do the ratio test for monotonicity to show it's decreasing. So I have this expression. So that'll equal n plus 1 all over 3 to the n plus 1 times 3 to the n all over n. That'll be n plus 1 all over n times 1 over 3. And so eventually 3 times n will be bigger than n plus 1. So just note, you know, n is n plus 1 will be less than n plus n for n greater than or equal to 1. And then n plus 1 will be, did I say greater than? I meant less than n plus n plus n. In other words, n plus 1 is less than 3n. So n plus 1 divided by 3n is less than 1. Okay, so this is definitely less than 1. In other words, it's decreasing. In other words, the thing is convergent. Okay, so hence convergent. Okay, okie dokie. So I can get an approximation for the thing, and I want to use the first 6 terms and figure out how good of an approximation that really is. Okay, so S sub 6, I'm going to go from n equals 1 to 6. So here I go. So plugging in 1, I've lost my stupid sequence of terms. So it's a series -1 to the n plus 1 times n over 3 to the n, starting at 1. Okay, so when n is 1, I get -1 squared, which is 1, times n, which is 1, all over 3 to the 1. Okay. Then it'll be minus, and n now is 2, over 3 squared is 9. And then plus, n is 3, all over 3 cubed, I guess, minus 4, all over 3 to the 4th. 6 over 3 to the 6. Okay. Okay, if you plop that into your calculator, you'll get 5/27, believe it or not. Okay. We want to know how good of an approximation that is. So from the estimation theorem, we know the difference between S and S6 will be less than or equal to 7 all over 3 to the 7, right? It's basically you just take the next term in line if you were figuring out S sub 7, and that's the way to see how good this is. So this thing is 7 all over, if you figure it out, it'll be 7 all over 2187. So the error is kind of small, 2187. In my world, it's kind of small. It's approximately, it's within 0.003, so 3 thousandths. You can also kind of wedge the actual solution. So you could say note S minus S sub 6, which is 5/27, must be in between 7 all over 2187, greater than -7 all over 2187. And then you could add 5/27 to all 3 sides and kind of figure out that the actual value of the sum is in between 398 all over 2187 and 412 all over 2187. Or you can get decimals approximations if you want. The other type of problem is where they want you to come in underneath some sort of error. So in this problem, we want to find the number of terms necessary in order to have error less than 0.001. Okay, so find number of terms necessary to have error. In other words, the difference between S and S sub n less than some value. In this case, we want less than 0.001. Okay, so the series they give us is going to be the sum from n equals 1 to infinity of -1 to the n plus 1 over n to the 5th. Okay. So we want S minus S sub n to be less than that 0.001. We know that S minus S sub n is less than or equal to A sub n, and A sub n is the portion without the -1 part. A sub n plus 1, of course. So you take 1 over n to the 5th and replace n with n plus 1. You get 1 over n plus 1 to the 5th. And then you need to make sure that this is less than 0.001. Okay. So what you do is usually just trial and error. So by trial and error, we let first n equal 1. You'll have 1 all over when you plug, and you're plugging stuff into that expression, a sub n plus 1 right here. Okay. So when n is 1, we'd get 1 plus 1 to the 5th, so 2 to the 5th. and approximating that's 0.03, so that's not good enough. So you go to n equals 2, you get 1 all over 3 to the 5th, which is 0.004. It's better, but it's not good enough. So try n is 3. So you get 1 all over 4 to the 5th, which is 0.00097, and that's definitely less than 0.001. So n equals 3. You need s sub 3, basically. So we need s sub 3, and of course if they ask for that, you can write it all out using the formula. So the sum was -1 to the n plus 1 all over n to the 5th from n equals 1 to infinity. So s sub 3, plug in 1 first, you get 1 all over 1 to the 5th, which is just 1. I don't know why I wrote 3. Just 1. And then minus 1 all over 2 to the 5th, and then plus 1 all over 3 to the 5th. For your approximation what the actual sum is. This is approximately 0.9729. Okay, so that is the first part, right? Where are we on time? So almost an hour to get through the first part. The second part then is on these things called conditional convergence and absolute convergence. Okay. So let's take a look. Okay, so what is the difference? Well, it's about absolute values of terms of a series. So compare this thing which is called the alternating harmonic series with the harmonic series. Okay, we know this guy is divergent. We know the harmonic series is divergent. What about this other guy? Is this guy divergent? And then notice the relationship between this two. This is actually just equal to the absolute value, the sum of the absolute value of the terms of the alternating harmonic series. Okay? So there's this kind of relationship. If you take the absolute value, you get this, and then you get this. It turns out if both were convergent, so if this first part absolute value, I'm going to make this more clear in a second, but if this first part absolute value of was convergent, it'd be called absolutely convergent. Okay. If this part is divergent, but then this part over here is convergent, it's called conditional convergence. Okay. So what was that again? If you're given a series, so given the series A sub n, if the series of the absolute values of the terms is convergent, then it's absolutely convergent. And it even implies also that the series of A sub n is convergent. If the series of the absolute value of the terms is divergent, but the series as it is originally is convergent, it's called conditionally convergent. Okay, so right now there's no way this is absolutely convergent because the series of the absolute value of the terms is just the harmonic series, which is divergent. Okay, but there's hope that this might be conditionally convergent if this thing converges. So let's consider that thing and see what happens. So we have the series n equals 1 to infinity of -1 to the n all over n. And first, we're using the alternating series test, so we take the limit of 1 over n, that's clearly 0. And then secondly, 1 all over n plus 1 all over 1 over n is equal to n all over n plus 1, and that's clearly less than 1. Okay, the numerator is less than the denominator for all n greater than or equal to 1. Hence, this thing is convergent. So what do we have? We have that overall, the series -1 to the n all over n is conditionally convergent. Okay. Okay, so the way you want to approach these problems is kind of in a flow chart. So the flow chart for dealing with these things. First, you're going to analyze the sequence of partial sums. Let's make this so I can actually, well, here we go. Okay, so you ask, so first you want to ask yourself, is the series of the absolute value convergent? Okay, it's a series where you take the sum of the absolute value of the terms. Is that thing convergent? Okay, question mark. That's a question mark. Okay. And if yes, then the series, the original series A sub n, is absolutely convergent. Okay, and of course, then the series is convergent as well. If you want to write that, you can. Okay. Absolutely convergent is kind of like a more powerful type of convergence. All right, and then no. If no, then you go and analyze the normal series as it's written. Is this series convergent? If yes, the series is conditionally convergent, like with the alternating harmonic series. If no, then the thing is divergent. Okay. So these problems can get pretty long if you end up with one of these that turns out to be divergent. It's quick sometimes, but let's take a look. Okay. So let's try this example. We'll make this one the video quiz. Let me put in my notes that this is the video quiz. So we're now on homework number 7. This is section 9.5, and we need to figure out whether this thing is absolutely convergent, conditionally convergent, or divergent. Okay. And the series is the series from n equals 1 to infinity of -1 to the n all over n factorial. Okay. I just mark that in my notes so I don't forget. Okay. This is going to be one of the easy ones, so I'm not worried too much. Okay. So on the flow chart, you start with the series of the absolute value, okay, of the terms. So start with the series of the absolute value of this -1 to the n over n factorial from n equals 1 to infinity. And of course, the absolute value will just get rid of those -1 to the n's. So we have n to the 1, n equals 1 to infinity of 1 over n factorial. So we want to see if this thing is convergent. Okay, we can. What kind of test do we need to do here? Well, some sort of comparison test, right? Probably. Yeah. Okay. Doing direct comparison. We note, and remember for direct comparisons, I want you to do 3 things. First, make your inequality. So first off, 1 over n factorial will be less than 1 all over 2 to the n. Okay, because n factorial it explodes. It'll be so big that 2 to the n will never catch up to it. Okay, and I went over that in the direct comparison test section, if you need to go back and look. Okay. Secondly, then I make a note about this series I'm comparing it to. So the series of 1 all over 2 to the n is a geometric series. It's convergent. And then why is it convergent? It's convergent because the absolute value of r is equal to 1/2, which is less than 1. Okay. Then thirdly, because the geometric series is convergent and it's above the series 1 over n factorial, they both converge. Okay. Okay, so going back to the flow chart, what we've done is shown that this thing converges. Okay, so yes, so therefore the series is absolutely convergent, so therefore the series is convergent. I'll just say absolutely convergent. Okay. Okay. So that was the video quiz. Okay. All right, let's move on to ones that are a little uglier. Series -1 to the n all over n ln n from n equals 2 to infinity. Okay, so first start with the absolute value thing. So start with the series of the absolute value of the terms, n times ln n, and this will be the series of 1 all over n ln n. Okay. This thing looks like we do an integral test on it. So note the integral test. And it's, I'll just assume it's decreasing, positive, and continuous. It's obviously positive and continuous is decreasing. You just take the derivative, yeah, and show it's less than 0. But let's go ahead and dive into the integral test. So it's the integral from 2 to infinity of 1 all over x ln x dx. We're going to need to do a u sub on this character. So u for ln x, and then du will be, ooh, that's not going to work, will it? Do I have to do by parts? Gee willikers. Well, it'll work. So this will be 1 over x dx, and then dx will be x du. So this will be, and we need a limit here as well, b to infinity, 2 to b. And then we have 1 all over x times u times x du, and then that'll be the limit as b goes to infinity of the integral from 2 to the b of 1 over u du, which is a natural log. So that's the limit as b goes to infinity of natural log of u, which is the natural log of x from 2 to b. And then that will equal the limit as b goes to infinity of the natural log of the natural log of b minus the natural log of the natural log of 2. As b goes to infinity, this inner part here inside the natural log will go to infinity. So it'll be something like 10, 100, 1,000, 1,000,000. So you're plugging something going to infinity inside the natural log, and that will make the natural log also go to infinity. Okay, so this whole thing will be infinity, and then minus some number L, which will equal infinity. In other words, both diverge. So hence, by the integral test, the series diverges. Okay, so where are we on the flow chart? I've started with the series with the absolute value. It's not convergent, so now I go back to the original series and see if that's convergent. Okay, so the original series, okay, so this is like the second part now. The original series is alternating. It's a series -1 to the n all over n ln n. So we do the alternating series test. First, the limit of 1 all over n ln n, that's clearly, as n goes to infinity, L over infinity, so that'll be 0. Secondly, then, you could do like a ratio n plus 1, 1 over n plus 1 times ln of n plus 1, all over 1 all over n ln n equals n ln n all over n plus 1 times ln of n plus 1. Natural log is increasing, so ln of n is going to be less than ln of n plus 1. N is also less than n plus 1, so the thing in the numerator will definitely be less than the thing in the denominator. In other words, that's less than 1. In other words, this thing is convergent. Okay. Going back to our flowchart then, where are we? So we've shown that this thing is not absolutely convergent, so we're over here. And then we noted that this thing is convergent, so we're in the conditional convergent category. Okay, so hence the series is conditionally convergent. Okay, let's do one that just is divergent and see how horrible that is. Example, the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n squared all over n plus 1 squared. All right, so again, we start with the series of the absolute value of that expression. So we have, that will just get rid of the negative 1 to the n plus 1. Okay. We can do an nth term test on this. So note the result of the nth term test. We take the limit of the terms of the series. And I knew that immediately it would be a good thing to take a limit of, because this is one of those ones where you can kind of just see what the limit's going to be, right? It's the same as the limit as n goes to infinity of n squared all over n squared plus 2n plus 1. So it'll be n squared over n squared, which is 1, which is not equal to 0. So hence, because it's not equal to 0, it's divergent. Okay. So from here we need to talk about whether it's conditionally convergent. So we go back to the original series. The series negative 1 to the n plus 1 times n squared all over n plus 1 squared. Going back to this thing, we note it's alternating. Right? So we try the alternating series test, and of course it's going to fail that first step. We just kind of already did it above. This will equal 1, which does not equal 0. You could then go to the nth term test. So technically you have to go to the nth term test. The limit of negative 1 to the n plus 1 times n squared all over n plus 1 squared equals two different things, depending on whether the terms are even or odd. So if the terms are even, then it's going to be negative 1. If terms are even. If the terms are odd, then it's going to be positive 1. In other words, the limit of the odd terms does not equal the limit of the even terms, therefore the limit does not exist. So by the nth term test, we notice this limit does not exist. And thus is not equal to 0. Okay, hold on one sec. Okay, so by the nth term test, we note that this thing, this limit does not exist, and hence it's not equal, and hence, my English is running down the drain, hence it is not equal to 0, and hence it's divergent. So basically we showed that the series with the absolute value on it is divergent. Then we showed the original series is divergent. Hence, it's just completely divergent. There's no absoluteness to it. There's no conditionalness to it. Hence, the original series is divergent. Okay. Basically, the deal with conditional and absolute convergence is you can rearrange terms if you know that something is absolutely convergent. Whereas with conditional convergence, you can't, when you're playing around with the sum, you can't rearrange things. So I mean, in one of the proofs, it seems like I'm doing some rearranging, but I'm not really. I'm just associating differently, right? Like in this S sub 2n thing, that's like associating instead of rearranging. I don't know. There's so I'm trying to think here. So an example, but no, I haven't really gotten into it. But that's the idea. It's something about you're able to rearrange the terms of the series, no matter how. If it's absolutely convergent, you can rearrange the terms however you want, and it doesn't affect things. So you can kind of pull these tricks, like I did with the proof of that alternating series test. Do that on steroids if you know it's absolutely convergent. Okay. With conditional convergence, you can't pull that out, and if you try, you can kind of get funny results happening, which make no sense. Okay, so I've not looked into it, but it's something you want to study on the internet by all means. Okay, so anyways, sorry, it's a long section. It's the way it goes. We'll call it quits there, and we'll see you next time.